In this tutorial, we'll be looking at different aspects of orbitals, and in this example right here we have 3px orbital. Now the very first number on the left is the principal quantum number n, which describes the shell or the energy level the electron is in. The next quantum number is the value L, which is the angular quantum number, which describes the subshell and the magnitude of the orbital angular momentum. Later on we'll see we also get the number of angular nodes from the value L. Next is the value m sub L, which describes the specific orbital within that subshell. Now the value m sub L can go from minus L all the way to plus L. And now we have the value n, which is the overall shell, then the subshell, and lastly the specific orbital within that subshell. Next we'll be looking at the orbitals, in this case S, P, and D, and the value L. So the value L is specific to these orbitals. In the case of S, it's 0. In the case of a p orbital, L equals 1. And in the case of a d orbital, the value of L would be 2. Now the value m sub L, as we said, goes from minus L all the way to plus L. Now in the case of an s orbital, it's just 0 that's available. In the case of a p orbital, we have minus 1, 0, and then plus 1. So we have plus, minus 1, and 0. In the case of a d orbital, we have plus minus 2, plus minus 1, and 0. And from these values, we can assign specific orbitals. So in the case of an s orbital, we only have the s orbital. In the case of a p orbital, we have 0 as the pz orbital. Now remember, the more you are towards the z orbital, the lower that number. So the ones that are orthogonal to the z orbital, px and py, would be assigned plus and minus 1. Same idea in the case of a d orbital, the 0 would be assigned to dz square, and then the values plus minus 1 would be assigned to dxz and dyz, and then plus minus 2 would be assigned to the orbitals that do not have any z component, that are dx square minus y square and dxy. Next, we will be looking at angular nodes. So we said that from the value L we can get the angular nodes. And the angular nodes are nodes that actually bisect through the plane of the orbital, and that does not have any probability of finding an electron. And it would change the phasing as well in that specific orbital, as we will see shortly. In the case of an s orbital, we do not have any nodes. In the case of a p orbital, we have the one node, and in the case of a d orbital, we have 2 nodes. Now, as you can see here, the node would be splitting the orbital in half, as in the case of a p orbital. In the case of a d orbital, we would have the orbital split into 4 lobes, as shown here. Now in terms of phasing, in the case of a d orbital, the phasing changes every 90 degrees. So the opposite lobes have the same phasing. In the case of a p orbital, we change the phase every 180 degrees, and so opposite lobes have different phasing. Now in the case of a radial node, the equation for a radial node is n minus L minus 1. So in the case of the example given above, 3px, we would have n equal 1 or n equal 3. L would be 1 because it's a p orbital, and minus 1 would give us an overall radial number of nodes 1. Let's start with drawing the px orbital by itself along the x-axis. Now it doesn't matter what axis you choose, y or z in this case, because the lobes would be along the x-axis. Now in this case here, we would have a line bisecting along the YZ plane. Now if you want to find the angular nodes, we'll see that momentarily, but let's draw the full orbital. In this case here, we're adding in the radial nodes. So we have one radial node some distance from the nucleus, and then the phasing would change. So what's phased inside the circle would be not phased outside the circle. Now we have the px orbital, and if we assign x to be equal to 0 and plot that plane, then that plane would represent the node. And that's one way you can use these m sub l values to actually draw these nodes before drawing the orbitals. Let's take a look at another example. So we have dxz. Now in this case here, we know it's a d orbital, and we know that the value of L is 2, so we have 2 angular nodes. Now the angular nodes are, if we set x equal to 0, we have a plane at x equals 0 and a plane at y equal 0. So the plane where x is equal to 0, it would be along the yz plane, and the other one would be along the xy plane. And so that's how we would use these nodes to help us sketch these orbitals. And if we have any radial nodes, it's the same idea. It's some distance away from the nucleus, and the phasing would change outside of that radial node. Let's take a look at another example, dx squared minus y squared. In this case here, we have x squared minus y squared orbital. So if we set that equal to 0, we can find out the nodes. So y squared would be equal to x squared in this case, and y would equal to plus minus x. Now these are easy lines to draw. So the y equal x would be just bisecting through the axes, going in the positive direction, and y equal minus x would be in the opposite direction. Now this is why dx squared minus y squared would be drawn or sketched along the axes, unlike dxy. In the case of dxy, the lobes would be between the axes. But in this case here, dx squared minus y squared, those lobes are drawn along the axes, and this is why. It's because the nodes are actually in between the axes in this case, y equal x and y equal minus x. Next, let's take a look at an example, dz squared. Now dz squared is just an abbreviation. The actual orbital in this case is 2z squared minus x squared minus y squared. And if we set that equaling to 0, then we would realize that the value z would be equal to half square root of x squared plus y squared. Now if you have done any vector calculus before, you would realize that this equation is a vector equation, and if you were to draw it out, it would look like a cone. Now since the nodes are cones, that means that the electron density would be around those cones, and this is why dz squared looks the way it does, in which case the lobes are up and down along the z-axis, and then we would have the donut shaped torus that is going along the xy plane. So in this video we covered orbitals, how to extract quantum numbers, how to sketch orbitals, how to figure out angular and radial nodes.